Let me show you something simple. Strike a match. Watch it burn. The wood turns black. The chemicals react. Heat and light pour out into the room, and when it's done, you're left with a charred stick and some ash. Now I want you to do something. I want you to unburn that match. Take the ash, take the smoke that dispersed into the air, take the heat that warmed the room and put it all back. Reconstruct the match exactly as it was before you struck it. Go ahead, I'll wait. You can't do it. Obviously, that's absurd. Burned matches don't unburn themselves. Fires don't spontaneously reverse and suck their heat back in. But here's what should puzzle you. Why can't you unburn a match? And before you say, because that's not how things work, let me tell you something. At the level of individual atoms, at the fundamental level where physics actually operates, every single collision, every single interaction, every single process that happened when that match burned could happen in reverse. The atoms don't care which direction time goes. The forces don't care. The laws of motion work forwards and backwards equally well. A carbon atom combining with an oxygen atom to make carbon dioxide, releasing energy, that process is completely reversible at the atomic level. You could have carbon dioxide absorbing energy and splitting back into carbon and oxygen. The physics allows it. A molecule vibrating and transferring energy to a neighboring molecule that works forwards and backwards. The equations don't distinguish, so if the fundamental physics is reversible, why is the world so obviously not? Think about memory for a moment. You remember yesterday. You remember last week. You remember your childhood, events that happened, conversations you had, places you went. But tomorrow, nothing. The future is blank, not fuzzy, not uncertain, completely absent from your mind. This seems natural. Of course you remember the past. Of course you don't remember the future. But why? What makes the past different from the future at a fundamental level? You can affect the future. You make decisions, you take actions, you try to change what's going to happen. You choose to raise your hand and your hand raises. You choose to speak and words come out. The future feels malleable, changeable, under your influence. But the past, it's fixed, unchangeable, done. You can regret it, you can wish it had gone differently, you can think about what you should have done instead, but you can't alter it, not even slightly. The past is written in stone. This asymmetry between past and future is so deeply embedded in our experience that we don't even question it. Past is different from future. Obviously, that's just how time works, but we should question it, because nothing in the fundamental laws of physics says time has to work this way. Take gravity. Newton's equation for gravitational force, the equation that describes how objects fall, how planets orbit, how trajectories curve through space. It's completely symmetric in time. If I show you a movie of a planet orbiting a star, you can't tell if I'm playing it forwards or backwards. Both directions show valid orbits. The equation doesn't know the difference. There's no variable in the equation labeled time direction. No arrow saying this way is forward. Same with electromagnetism. Maxwell's equations, the ones that describe how electric and magnetic fields behave, how light propagates, how charges interact, they work perfectly well in both directions. A light wave spreading out from a source could just as easily be mathematically a light wave converging toward a sink. Run the equations backwards and you still get valid solutions. The physics doesn't care. Nuclear forces, the strong force that holds atomic nuclei together, the weak force that causes radioactive decay. Even there, at the quantum level, the fundamental interactions are reversible. For every process, there's a time-reversed process that's equally valid. So where does the arrow come from? Where does this fundamental difference between past and future originate if it's not in the laws themselves? Take a glass of water. Clear, still water, room temperature. Nothing special about it. Now add a single drop of ink, black ink, right in the center. Just let it fall from a dropper. What happens? The ink spreads, it diffuses outward, tendrils extend through the water, dark wisps curl and twist. And after a while, maybe a few minutes, maybe an hour, depending on how still you keep it, you have uniformly gray water. The ink has spread everywhere evenly. Now wait for the ink to spontaneously gather back together. Wait for all those dispersed molecules to find their way back to the center and form a single drop again. You'll be waiting forever. But why? Think about what's actually happening at the molecular level. Each molecule of ink is just moving around, jiggling because of thermal motion, bouncing off water molecules, random walk, Brownian motion. There's no force pushing ink molecules away from each other. There's no repulsion between them. They're just moving randomly. So if the motion is random, if each molecule has an equal chance of moving in any direction, why don't they all randomly move back toward the center at the same time? Why don't we ever see the ink unmix? The answer is probability. It's about counting arrangements. When the ink is concentrated in one drop, when all the ink molecules are clustered together in a small region, there's only a limited number of ways the molecules can be arranged while still looking like a concentrated drop. Sure, they can be arranged differently, this molecule here, that molecule there, but they all have to be in roughly the same location. So the number of arrangements is limited, maybe billions, maybe trillions. Sounds like a lot. But when the ink is spread throughout the water, when it's uniformly dispersed, when there's a little bit of ink everywhere, there are vastly more arrangements. Not just more, incomparably more. Any molecule can be anywhere in the glass. And as long as the overall density is uniform, as long as there's roughly the same number of molecules in any given region, it looks the same to you. Uniformly gray. The number of arrangements is not billions or trillions. It's a 1 followed by so many zeros that the number itself is larger than anything you can comprehend. More zeros than there are atoms in the observable universe. So when molecules move randomly, when they jiggle and bounce and drift, they're exploring different arrangements. They're sampling the space of possible configurations. And there are so many more ways to be spread out than to be concentrated that they almost inevitably end up spread out. Not because spreading is favored, not because there's a force pushing them apart, but because there are more dispersed arrangements to be in. It's not that unmixing is forbidden. It's not that there's a law against it. It's just staggeringly, overwhelmingly, crushingly unlikely. This is what we mean by entropy, and I want you to understand this clearly because it's crucial. Entropy is not just disorder. That's a rough way of thinking about it, and it's useful sometimes, but it's not quite right. Entropy is a measure of how many different microscopic arrangements produce the same macroscopic appearance. It's a count, a number, a specific quantity you can calculate. The concentrated drop of ink has low entropy. Why? Because there are relatively few ways to arrange the molecules and still have a concentrated drop. The arrangement is constrained, specific, limited. The dispersed, uniform gray water has high entropy. Why? Because there are enormously many ways to arrange the molecules and still have uniform gray water. The arrangement is unconstrained, flexible, vast. Low entropy equals few arrangements. High entropy equals many arrangements. That's the definition. And here's the key insight that explains everything. Systems naturally evolve from low entropy states to high entropy states. Not because of a law, not because there's a rule saying entropy must increase, but because of probability. Pure probability. If you're in a state with few arrangements, a low entropy state, and you let the system evolve randomly, where are you most likely to end up? In a state with many arrangements, a high entropy state, because there are more of them to land in. This is the second law of thermodynamics. Entropy increases. Not always, not at the microscopic level where fluctuations happen, but statistically, overwhelmingly, for any macroscopic system. Things spread out, things mix, things fall apart, ordered arrangements become disordered, concentrated distributions become dispersed, low entropy becomes high entropy. But notice what I just said. Systems evolve from low entropy to high entropy, from past to future. That's a direction, that's an arrow pointing one way through time. And suddenly we have an answer to our question. The arrow of time, the fundamental difference between past and future, comes from entropy. The past is the direction of lower entropy. The future is the direction of higher entropy. That's it. That's what makes them different. You remember the past because your brain is a recording device. And recording information requires creating order, requires low entropy structures. Your memories are physical. They're patterns of connections between neurons, states of molecules in your brain, configurations of proteins. All of this requires organized arrangements, specific structures. Low entropy, the past can be recorded because it had more order, more structure. Lower entropy, there was something to record. You can't remember the future because the future hasn't been organized yet. The entropy will be higher, the information will be more dispersed. There will be nothing specific to read, nothing structured to recall. The asymmetry of memory, the difference between remembering yesterday and not remembering tomorrow, comes from the asymmetry of entropy. This is happening constantly, everywhere around you, every moment of every day. You just don't notice it because it's so relentless, so universal, so absolutely consistent that it becomes invisible. You light a candle, the wax burns. What's really happening? Chemical energy stored in organized molecular bonds, carbon and hydrogen atoms arranged in long chains. That energy gets converted to heat and light. The heat disperses into the room, spreads out in all directions. The light radiates away. The organized chemical energy becomes disorganized thermal energy. Entropy increases. The candle will never unburn itself. The heat will never flow back into the candle and reform the wax. The chemical bonds will never spontaneously reassemble because that would require entropy to decrease. And it doesn't. You crack an egg. The shell breaks. Pieces scatter. The yolk spills out. The membrane tears. The white spreads across the surface. What was contained is now released. What was structured is now chaotic. What was organized is now dispersed. Entropy increases. Could the egg uncrack? Could all those pieces fly back together? Could the yolk and white retreat back into the perfectly shaped shell? In principle, yes. Every atom could reverse its motion. Every force could act in reverse. The laws allow it. But the probability is so small that it will never happen. Not in the age of the universe. Not in a trillion ages of the universe. The number is so tiny, it's effectively zero. Your coffee cools down. You pour it hot. You leave it on the table. And slowly, inevitably, it cools. What's happening? The coffee is hot. The room is cool. Heat flows from hot to cold. Always. The thermal energy in the coffee spreads out into the room. The concentrated energy becomes dispersed. Eventually, the coffee and the room reach the same temperature. Equilibrium, thermal equilibrium. No more flow. Maximum entropy for this system. The coffee will never spontaneously heat back up. Heat will never flow from the cooler room into the warmer coffee. That would decrease entropy. And entropy doesn't decrease. Every time something breaks, entropy increases. Every time something wears out, entropy increases. Every time something mixes or spreads or dissolves or decays or burns or melts or evaporates, entropy increases. And you never see it go the other way. You never see heat flowing from cold to hot. You never see broken glass assembling itself. You never see scrambled eggs unscrambling. You never see smoke gathering back into wood. Not because these things are forbidden, not because there's a cosmic law with a big stop sign, but because there are vastly more ways to be broken than whole. More ways to be mixed than separated. More ways to be spread out than concentrated. The universe is not moving toward disorder because disorder is better. It's moving toward disorder because there are more disordered states available. It's pure statistics. Overwhelming, inevitable, crushing statistics. But wait, if entropy always increases, if everything always moves towards more disorder, then why is there any order at all? Look around you right now. There are trees growing outside, buildings standing, cars running, stars shining in the sky. Your brain is functioning with incredible precision. Billions of neurons firing in exact patterns, thoughts forming, ideas connecting, consciousness existing. How is any of this possible in a universe that's supposed to be falling apart? How can there be any structure, any organization, any complexity if entropy always increases? The answer requires us to look back, way back, to the very beginning, to something we don't fully understand. The universe started, for reasons that remain mysterious, in a state of extraordinarily low entropy. The Big Bang wasn't just hot, wasn't just dense. It was organized, ordered, structured. All that energy and matter packed together in an incredibly tiny volume existed in a very specific configuration, not a random configuration, not a high entropy mess, but a low entropy, highly ordered initial state. And ever since then, for the last 14 billion years, entropy has been increasing. The universe has been unwinding, moving from that initial order toward eventual disorder, spreading out, cooling down, becoming less organized. So when you see a tree, when you see something growing and organizing and becoming more complex, you're not seeing order being created from nothing. You're not witnessing a violation of entropy increase. You're seeing the delayed release of order that was there from the beginning. You're seeing potential that was loaded into the universe at the Big Bang finally being spent. The tree grows by absorbing sunlight. That sunlight is low entropy energy. How? Because it's organized. It's coming from one direction. All the photons are aligned, all moving roughly the same way, all coming from the sun. That's order, that's structure, that's low entropy. The tree uses that energy to power chemical reactions, to build cellulose, to create cells, to arrange molecules into complex structures. The tree itself becomes more ordered, but that's not the end of the story. The tree also radiates heat. In all directions, random thermal radiation, high entropy energy, disorganized, scattered. And if you do the accounting carefully, if you add up all the entropy changes, the total entropy increases, always. The entropy decrease in the tree is more than compensated by the entropy increase in the radiation. The tree's order is borrowed, temporarily on loan from the low entropy sunlight. You're the same. You are not fighting entropy. You're not defying the second law. You are participating in it. You eat food. Food is organized. An apple has structure, specific molecules in specific arrangements, proteins folded just so, sugars stored in ordered patterns. Low entropy. Your body breaks down that food, digests it, extracts the energy, uses that energy to maintain itself, to build new proteins, to repair damaged cells, to send electrical signals through neurons, to move muscles, to think thoughts. All of this maintenance, all of this activity, all of this life requires energy. And using energy produces entropy. You exhale carbon dioxide, you radiate heat into your surroundings, you produce waste, all of it high entropy, all of it more disordered than the food you consumed. Do the full accounting, track every molecule, add up every entropy change. And the total always increases. The order in your body, the incredible complexity of your biological machinery is borrowed, on loan, maintained by constantly increasing entropy elsewhere. The food you ate got its order from sunlight absorbed by plants. The sunlight got its order from nuclear fusion in the sun. The fusion reactions got their order from gravitational collapse of a gas cloud. The gas cloud got its order from the slightly non-uniform density fluctuations in the early universe. And those fluctuations trace back to the low entropy initial conditions of the Big Bang itself. You are connected to the Big Bang, not metaphorically, not spiritually, but literally, physically, through an unbroken chain of entropy increase stretching back 14 billion years. Every thought you think requires energy. Neurons firing consume glucose, consume ATP. Energy flow produces heat. Heat increases entropy. So every time you think, every time you make a decision, every time you remember something or imagine something or feel something, you're increasing the entropy of the universe. You are an entropy increasing machine, a very complicated, very interesting, very conscious entropy increasing machine. But fundamentally, that's what you are. Life doesn't violate the second law of thermodynamics. Life is what the second law looks like when it gets sufficiently complex. When entropy increase happens in a way that produces structure temporarily before ultimately dispersing it. Now we can answer the question we started with. Why does time have a direction? Why is the future different from the past? Because the past had lower entropy. The future will have higher entropy. That's it. That's the entire answer. The laws of physics don't care about time direction. You can run the equations forwards or backwards and they work equally well. But we care. We have to care because we're made of atoms in low entropy configurations, and low entropy configurations are unstable. They're temporary. They're unlikely. They evolve. They change. They move toward higher entropy because there are more high entropy states available. That evolution, that change, that inevitable drift from ordered to disordered is what we experience as time passing. The match burns and doesn't unburn. The ink disperses and doesn't gather. The egg breaks and doesn't unbreak. Your coffee cools and doesn't reheat. Entropy increases, always. And that increase, that asymmetry, that one-way flow, is the arrow of time. You can't unburn a match because that would require entropy to decrease. And entropy doesn't decrease, not spontaneously, not macroscopically, not ever. Could you, in principle, arrange every atom, every molecule of smoke, every quantum of heat, every bit of dispersed energy back into the exact configuration of an unburned match? Could you reverse every collision, every interaction, every process? In principle, yes. The laws allow it, the physics permits it, but the probability is so staggeringly small, so vanishingly tiny, so incomprehensibly unlikely that it would take longer than the age of the universe. Much, much longer. So long that the timescale itself becomes meaningless. So the match stays burned, time moves forward, entropy increases, and we experience that as the passage of time. Where does this lead? Where is the universe going? Eventually, given enough time, given trillions and trillions of years, the universe reaches maximum entropy. Everything spreads out, everything equalizes, everything reaches equilibrium. All the stars burn out, all the black holes evaporate through Hawking radiation, all the energy gets distributed uniformly throughout space, perfect equilibrium, perfect disorder, maximum entropy, heat, death, the ultimate fate of the universe. Nothing more happening, nothing more changing. No temperature gradients, no energy flows, no structure, no complexity, just uniform, featureless sameness extending forever. The same everywhere, the same always. Nothing to distinguish one place from another, nothing to distinguish one moment from another. Some people find this depressing. Everything ends, everything falls apart. No matter what you build, no matter what you create, no matter what you accomplish, entropy will eventually take it all apart. Every star will die, every civilization will crumble, every thought will fade. All of it eventually dispersed into the heat death. But I don't see it that way, because the fact that entropy increases, the fact that time has a direction, this is what makes anything interesting happen at all. Without entropy increase, without the arrow of time, without the flow from low entropy to high entropy, the universe would be static, frozen, equilibrium forever. Nothing would change, nothing would happen, no events, no moments, no experiences, no life, no consciousness, no anything. The arrow of time is what gives us moments. The march toward disorder is what gives us change. The slow unwinding from the Big Bang toward heat death is what gives us everything in between: stars, planets, life, thought, existence itself. You exist because the universe started with low entropy. You experience time because entropy is increasing. You can remember the past because it had more order. You can't remember the future because it will have less order. Every match that burns, every egg that breaks, every cup that shatters, every breath you take, it's all moving in the same direction, toward higher entropy, toward more disorder, toward the eventual heat death of everything. But right now, in this moment, the universe is still ordered enough for stars to burn, for planets to exist, for molecules to arrange themselves into living things, for you to be conscious and thinking and wondering about all of this. The universe started with low entropy. It's winding down. It will eventually reach maximum entropy and stop changing entirely. But between the beginning and the end, there's this window, this era, this brief cosmic moment where complexity is possible, where structure can exist, where entropy can increase in interesting ways. And you're in that window. You're part of that moment. You're riding the wave of entropy increase from the ordered past toward the disordered future. That's not tragedy. That's opportunity, that's meaning, that's everything. So yes, you can't unburn a match. You can't reverse time. You can't decrease entropy. The arrow points one way, and that one-way arrow is what makes now matter.